right, let's take a look at the answers from um, sections 10.1 and 10.2. We'll be covering 10.3 and 10.4 next week. But problems that you were asked to do really were just 10.1 and 10.2. That's what the quiz will be over tomorrow. So don't freak out if you didn't know how to do 25 through 48 because we haven't talked about those theorems yet. But we will. We will soon. I wonder what they'll be. We'll find out. 10.1, you were basically like naming things. You were giving examples of these. I can just tell you to be really careful that your notation matches what you're talking about. For example, a radius, which is a line segment that starts at the center of a circle, and the other end point is a point somewhere on the circle, is a segment. If you don't have the segment notation, it's wrong, even if your letters are correct. The notation is part of what makes it correct. You can't just say, oh, the letters are all I need, because it's wrong. Now, a tangent, unless it specifies that it's a tangent segment or a tangent array, a tangent is defined as a line. We saw that in our definitions a couple of days ago. So you need to have the line notation. Notice that AF is a common tangent because it's a tangent to both circles B and K simultaneously. A secant is also a line, so you have to have the right notation there. There are things called secant segments that you'll talk about, but right now this just said secant. Secant is defined as a line. Centers of circles are points. Points of tangency are single points. Points are just points. You name them with a single letter. Make sure it's a capital letter, and you're good to go. Chords, once again, are line segments. They're defined as line segments that have both endpoints on a circle. So HG, segment HG would be a chord segment. JF or FJ would be a chord. And then a diameter is a chord, but it's a chord with a very special property. It goes through the center of the circle. So, chord FJ was also a diameter. So those are your answers for this. By the way, it did say give an example. So on some of these problems where I gave multiple answers, you only have to give one of them. You are just giving an example of one of these things. That takes us to problems 9 and 10. So when we went over this theorems on Tuesday, we did a problem just like this with the tangent segment creating the right triangle. In the homework for Tuesday night out of the book, we did 3 problems just like this. I mean, the setup was the same. The numbers changed a little bit. The key that we continue to talk about is algebraically, you have to know how to square a binomial, right? R plus 3 squared is not R squared plus 3 squared. It's R plus 3 times R plus 3. It has to be FOILed out. R plus 2 squared, same kind of deal. So numbers change, but the strategy stays the same. Tangent segments are perpendicular to the radii drawn. So we get these right triangles, and we can use the Pythagorean theorem, and everybody's happy. Don't worry that problem 9 here is a fractional answer. Not every answer is an integer, and not every answer is even a rational number. Sometimes you may be taking square roots of things that are not necessarily perfect squares. Numbers 11 and 12 are based not on theorem 10.1, the previous 2 problems, but on theorem 10.2. Tangent segments from a common point outside of a circle are congruent to each other. They have the same length. And so you just have to set them equal to each other. I didn't set this one up probably because it's, nobody ever really asks about it. But we could write it out really quickly. This would be 2x plus 7. Okay, has to have the same length as 3x minus 5 because, right, because these two tangent segments originate from the same point. And so that would solve to be x equals 12. 12 is a little more interesting because you end up with a quadratic equation. You're going to see a lot of quadratic equations in chapter 10, more so the second half of the chapter. But this one is a quadratic equation. Now, once these x's cancel, it's a simple quadratic equation because you don't have an x term, you just have an x squared term. So whenever you have that set up, you can simply solve for x squared like we did here, and then take the square root. Now, this is one of those situations where you're going to really have to pay attention. Whenever you take the square root, it doesn't matter if you have x squared equals 9 or x squared equals 10 or x squared equals 4/9. You're always going to get a positive root and a negative root, plus or minus 3, plus or minus root 10. In this case, plus and minus 2/3. A lot of the time, you end up throwing the negative out because it creates, when you plug it in, it creates a negative distance. But you always have to check. And in this case, 2/3 is such a small number, it doesn't, negative 2/3 does not create a negative distance. When I plug 2/3 in, and by the way, 2/3 squared, as we saw down here, is 4/9, right? So the 2/3 squared would be 4/9, and the 9s would cancel. You would just get 4 plus 2/3 plus 1, or 5 and 2/3. Well, 5 plus 2/3 is also 5 and 2/3. So 2/3 checks out. But what happens when I plug negative 2/3 in? Well, negative 2/3 plus 5 is 4 and 1/3. Now, the negative 2/3 squared would still turn into a positive 4/9 because negative times a negative is a positive. So you get a 4, and then that would make it a 5. But then the 5 and the negative 2/3 takes it back down to 4 1/3 again. So both answers work and give you positive distances, so you have to keep them both. And what that means is if you do all of this work and you forget that negative, you just lost half the credit on the problem because you only gave half the answers. So you've really got to understand the algebra behind this. 13 is the same premise. These two tangent segments are congruent. The x minus 1 squared is not just x squared minus 1, right? It has to be FOILed out. And the nice thing here is that once you do FOIL it out, the x squareds cancel out. So you just get a linear equation, and x is equal to 4. This guy over here, you have to kind of think through it a little bit. PS and QS are congruent because they're common tangents, or not common tangents, but tangents from a common point to the same circle. Likewise, QS, that was really bad, QS and RS have to be congruent because they're common tangents to circle B, okay? And so by the transitive property, because PS and RS are both congruent to the same segment, QS, they have to be congruent to each other. And so that's why we're allowed to set these equal to each other. Okay, so I think most of you guys probably did set them equal to each other. I'm not sure if you knew the actual reason why you were allowed to do that. It has to do with transitive property. It does freak some people out that you get, -1 as an answer. Once again, you can get negative answers. They just can't create negative distances. Distances have to be positive, but answers don't have to be positive. And so all we have to do is make sure that when I plug a -1 in up here, I don't get a negative distance. And this would be -4 plus 7, which would still be +3, and this would be -6 plus 9, which would still be +3. So first of all, they're equal. So we did the algebra right, and second of all, they're legitimate. They gave us positive answers. So that brings us to arcs. Section 10.2 is about arcs, different types of arcs and how to measure arcs. And this wanted you to do two things. It wanted you to determine whether it was a minor arc, a major arc, or a semicircle, and it also wanted you to determine the measure of the arc, find the measure of the arc. And so here are the answers. What I would do on these is just take the 1 minute it would take and just kind of label the things, because then all you have to do is add and subtract to get all your answers. I always identify diameters because they're very helpful. You have a diameter here and a diameter here. And think about what that does. It creates a 180-degree linear relationship here. So you get 105 through subtraction. It creates vertical angles here. So you get a 75. It creates a linear relationship across these three angles here. And so if the angle AGB is 75 and angle EGD is 30, we can subtract those from 180 to get 75 there. And then once you have those central angles, remember they're central angles because the vertex of these angles is all at the center. That means the corresponding arcs, right, are the same. So there's a one-to-one relationship with central angles. And now you're just, like I said earlier, adding and subtracting. What is, ED? Well, we already knew that was 30. What is EB? Well, that would be from E to B. Now, it's just two letters, so it's the short way, right? But that would be 75 plus 75, or 150. Could have also done 180 minus 30 and used the semicircle. What is EC? So this time, we're going from here to here. So that would be 30 plus 75 and so on. It really does help to trace these, because sometimes if you do them too fast, you don't read them correctly. For example, BEC, sometimes people will start at the wrong point or end at the wrong point or go the short distance. BEC is definitely either a semicircle or a major arc because it's three letters. So start at the beginning, hit that middle letter, and then end at the end point of the arc. The easiest way to do this one, instead of adding these four arcs, would be 360 minus 105, right? This problem's really the same, except they don't give you the picture. You have to kind of create it. So it tells us that angle, or circle C, has an arc that's 50 degrees, that there's a point that bisects that arc, and that there's a diameter. I would start with the most important thing, that there's a diameter. So here's my diameter. That diameter is called AE. So I'm going to go ahead and label A and an E. So that immediately gives me two semicircles, 180 up here, 180 down here. Now I can go ahead and play around with the points a little bit. I got a point D, so that arc AD is 50 degrees. It tells me that point B bisects that segment. So half of 50, right, would be 0.5. So I get a couple 0.5s in here. And once again, this was point B. And then finally, we can label the rest of it. So we'd have 180 minus 50, right, is 130. And we would have, of course, our semicircle below would be 180 degrees for that. And once you have your stuff labeled, these problems become very simple. AED is from A. Now it's three letters, so that means I have to go through E first before I get to D. The easiest way to do that is what? 360 minus 50. So that's where the 310 comes from. BD becomes very simple. It's just 25, right? Half of 50, and so on. So that's how I would do that one. If they give you information but they don't label anything, I would always draw a picture. Okay. You didn't have to do the next 24 problems, but you did have to do 37, which on the surface looks a little tricky because it's like, all right, they uh, they give me a circle with a radius of 3, and they ask for this little piece, and this little piece isn't even in the circle, right? dB. So that's what I think makes this kind of confusing. It's like, how the heck am I supposed to find that little chunk there? But we know quite a bit about the circle. First of all, we know that in any circle, every um, every tangent to a radius drawn to the point of tangency is perpendicular. That's what theorem 10.1 tells us. And so we get a right triangle, right? And in fact, this is your favorite right triangle. It's the good old 3, 4, 5. So hopefully most of you guys didn't have to use the Pythagorean theorem there, right? But we also know that in any circle, every radius is the same. That's the definition of a circle, basically. And so there you go. This segment right here, CB, has a length of 5, and this chunk right here from C to D is 3. So this is a subtraction problem, 5 minus 3. And so if you think about it the right way, this problem is quite simple. Finally, problem 38, which a couple people did ask about, and I don't know if this was more of a problem with the algebra or more of a problem with the conceptual setup. But here's the deal. Conceptually, it's pretty straightforward. The circle is divided into 3 arcs. Arc LN, arc NM, and finally arc ML. And some people would say, well, look, those are all 120, right? 360 divided by 3, but it doesn't tell me anywhere that those arcs are congruent to each other. And so all I really know is that they're non-overlapping arcs, so together they have to add up to 360 degrees. And that's where I would start this problem, is just taking the 3 arcs, right? So we've got, once again, 10x and 5x plus 36, right? And the x squared. I'll just add those 3 arcs together and make a little algebraic equation. Set up, the 360. Now, this is where I think if you did this right, then you're definitely on the right track. But this, I think, is where some people may have run into some problems because they forgot how to solve a quadratic. If the quadratic has an x squared, it has to have an x squared term to be a quadratic. But if it has an x term, you really need to set it equal to 0 almost no matter what. So I have to subtract the 360 over. Now, you haven't seen a quadratic in a while. I mean, they may have popped up a couple times in first semester, but not very often. You'll see so many more quadratics in chapter 10 than the rest of the book. It won't even be funny. But if you have just an x squared, you can just solve for x squared and take the square root of both sides. But if you have an x squared and an x, you're really going to be confined to a couple strategies that you learned about in Algebra 1. Okay, they all involve the same first step though, and that first step is you've got to set it equal to 0. None of the steps work, okay, if you don't do that. The tech step, the tech way of doing it, and you'll do this a lot in Algebra 2, is to graph it on your calculator, and you'll get a parabola, and then you look at see where your parabola is equal to 0. 0 is the roots. We call those the roots where it crosses the x-axis when y is equal to 0. And so that's the way that you'll do a lot in Algebra 2, especially when the answers are not integer values. But the way that we do it algebraically, the 2 main ways that we do it algebraically are the way that I would suggest you do it, which is factoring, or to use the quadratic formula, right? You learned about the quadratic formula in Algebra 1. You had a adventurous teacher that may have even showed you how to derive it, but if you have a quadratic in the form of ax squared plus bx plus c, and once again, it has to be set equal to 0. Then the quadratic formula will solve the roots for you if the real roots exist. In fact, it'll even solve imaginary roots, which is something you haven't learned yet. You'll learn about those in Algebra 2 as well. There's a little song, and I'm sure you remember it. It goes something like x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, if you recorded that and you try to put it online, I will find out about it, and I will take 50 points off your next quiz score. So please don't do anything cruel like that. But anyway, let's look at how this would look if you used a quadratic formula. Once again, it doesn't work unless you set it equal to 0. So you got to set it equal to 0. Once you have it set equal to 0, we can read, a is, with the x squared, that's 1. B is with the x, that's 15. And c is the constant, which is negative 324. And after that, we just plug them in, right? B is 15. Sometimes B is negative, and I see some people that think that, this negative covers the negative, and it doesn't. If B is negative, you get a negative something, and it'll actually, cancel out and turn positive. But in this case, B is positive, so we get negative 15 plus or minus the square root of some b squared is 15 squared minus 4 times a is 1 times c is negative 324. 4 times 1 times negative 324 is negative 1296. And so this is where we're going to get a double negative, which makes a positive, right? I'm going to be real honest. I usually, as soon as I see that I have 2 minus signs, 1, 2, usually go straight to the step because I know those 2 minus signs are going to produce a positive. Now, if all of these values are positive, it's going to stay minus. If 2 of these are negative, we'll get a positive, but then the negative will subtract it. So I usually just look how many negatives I have and then decide whether it's going to be addition or subtraction within the square root. Okay. If you get subtraction, like if I got subtraction in this case, if this ended up being minus, I'd be in big trouble because I'd get 225 minus 1296, which would be a negative. I'd be taking the square root of a negative number, which is what we call an imaginary number. And so this would have no real solutions. And once again, you'll learn about that in Algebra 2. These are big numbers, You typically, the problems you see don't have quite as big a numbers as these, but 1521, although you probably don't recognize it, is the calculator will tell you it's a perfect square. So that definitely makes us happy. Not indifferent, happy. I don't know what's going on here. There we go. Now you do have to break it into the 2 cases because remember we're doing plus or minus. So this is the the plus case, and I get 24 over 2, which is 12, and this is the minus case, when I get negative 54 over 2, which is negative 27. So the 2 answers are negative 27 and 12. If I graphed it, that means way back at negative 27 and somewhere over here at positive 12, this graph would have the roots. It would cross those 2 values, and you get the same answer if you graphed it, doing it this way. I would not do it with the quadratic formula unless you were really stuck with the factoring. I think factoring is the way to go, and it's really the way you're going to want to handle these things moving forward. So after you set it equal to 0, what I would do if I was you is I would create 2 parentheses. I'll go ahead and draw this out for you. I would create 2 parentheses like so. And then I would ask myself, all right, how am I going to get, an x squared? Because remember when we FOIL, the first times the first is what gives me that x squared. Well, this one, pretty simple, right? X times x is the only way to get x squared. if that was a 2x or a 3x, it would still be pretty easy because it would have to be x times 2x or x times 3x. It gets a little more interesting if it was like a 12x squared, because then it could be x times 12x or 2x times 6x or 3x times 4x. And I'm not going to give you any that are really nasty like that, but that's when you start wanting to use some more creative algorithms like this one called the California method. And if it really comes up and you guys ask me about it, I can do a little video on the California method. Now these two numbers right here, this one times this one, these are the lasts, right? So in FOIL, the first value comes from the firsts, and the last value, I guess that would be down here, wouldn't it? Comes from the lasts. So what two numbers are going to multiply to equal negative 324? All I really know is to multiply to get a negative, I need a positive and a negative. But 324, once again, is a bigger number than we normally see in these problems. And it's, you know, it's worth just starting at 1 and start multiplying, you know, dividing 324 to find factors until you figure out which two would have a difference of 15, because then you would know that those are the numbers you're looking at. So 1 times 324 does not have a difference of 15, and 2 times 162 doesn't, and 3 times 108, that's a difference of 105, so that's still way too big. We're looking for a difference of 15, right? 4 times 81, 77, so it's still too big. Now, if you divide 324 by 5, it doesn't go in, but 6 does. You know, a lot of people just do most of this on their calculators, which is fine, but there's easy ways of doing it. You know, if I want to know if 6 goes in, what I really want to do is I want to look and see if 3 goes in, okay? And if I have to double 3 to get to 6, I would have to have 108 to get, you know, the other factor. And so if 108 is even and I can cut it in half, then I know that it's divisible by 6. That's really the easiest way to do it once you start making your list. So just a little hint there. But the difference between 6 and 54 is not 15, right? It's 48. 9 times 36. By the way, here's a little trick for you. This works with 3s and 9s. If I add 3 plus 2 plus 4, if I add 3 plus 2 plus 4, I get 9. And 9 is divisible by 9. So I know that 9 goes into 324. That divisibility check where you add the digits of the number works for 3s and for 9s. So you may have learned that one from a previous math teacher. The difference here, though, is 27. So we're getting closer to 15, but we're still too big. Remember, 6 went in, right? So if I doubled 6 to get to 12, I would have to have 54, which I can't do because it's even. So 12 times 27 would work. And oh, wait. What's the difference between 12 and 27? 15. So there's the numbers that we were looking for to finish this problem. You know, the middle term here is positive, so we would make the bigger number the positive and the smaller number the negative. And if you foiled this out, it would get you back to this trinomial, right? X times x is x squared. 27 times negative 12 is negative 324. And then the middle terms would be 27x and negative 12x. And that's where the negative, positive 15x comes from. Okay. So this is an atypical problem in that the numbers are a little bigger. By the way, 324 is a perfect square, so 18 and 18 would work, but that was not the right combination of values. The zero property is a property in which we say if I multiply two numbers together, a times b, and the answer is 0, the only way that can happen is either a is 0 or b, b is 0, or maybe they're both 0. But you have to multiply by 0 to get an answer of 0. So when I multiply this thing by this thing, and the answer is 0, one of these two dudes has to be a 0. So what makes you know, x plus 27 into a 0? Negative 27. What makes um, x minus 12 into a 0? 12. So those are your two answers. If you notice, it's the exact same two answers we got doing it the quadratic formula method. Now, the negative 27, if we check, has to be thrown out, because if I plug negative 27 in, say, you know, right here, 10 times negative 27 is negative 270. We can't have negative angle measures. And so only the positive 12 sticks around. Once we know that 12 is the answer, we can come back up here and plug it in individually to each of the arcs and get their individual measurements, and then you're done with the problem. Make sure you label. You know, you don't want to just start randomly doing work and not say, you know, how it relates to the problem. So measure of arc LM, measure of arc LN, measure of arc MN, just like you used to do with angles for semester. Okay, so I think I spent half this half of this explanation going over just one problem, number 38, and most of that was not even the geometric relationship about the arcs adding up to 360. It was really more about, you know, the algebra of how you solve a quadratic. But hopefully it was worth it, because like I said, you'll see more quadratics in the future, and you'll definitely have to solve them coming up in the next couple weeks. I may have to do a little mini lesson just on reviewing and solving quadratics, but hopefully it's got you off on the right track. So there'll be a quiz posted tomorrow. I'll probably put it up around noon. And then I'll have like a 3-hour window for you to take it. You know, if it's a 30-minute quiz, that should give you a lot of flex time in that 3-hour window. So if you have to work around other classes and stuff like that, you're good to go. Just make sure you get it done by the end of the deadline. Otherwise, you'll lose points for being late with your quiz. It'll be kind of like your last quiz, Google form, and a lot of multiple choice questions, maybe a couple short answer, and you know, it'll be very similar to the problems you've been seeing in your homework. So if you have any questions from this worksheet, you're welcome to ask me. There were about 10 of you, I think, that didn't submit the homework. Remember, this one, you're attaching the file to the Google assignment and submitting it. So you need to do that as soon as you watch this in the morning. I'll send a reminder out for people that forgot. I'm not going to collect the homework often, but I'll definitely put a note where you need to get it turned in when I am going to look over them. Good luck on your quiz, and I hope you have a good weekend. And congratulations on surviving your second remote week of learning. And I know we got another like 4 of them to get through April. Hopefully things start moving in the right direction by the end of April.